All right, so once again, welcome back to another exciting day of mathematics. Warm-up number 45 is on your screen, and it reads, number 1, compute the sum, difference, and product of 15 minus 3i and 11 plus 5i. We've been doing these. Hopefully today will be a little bit more automatic. Number 2, solve and allow for imaginary numbers. Quadratic equation given reads 2x squared plus 48 equals y. Number 3, graph f of x equals x squared without a table. Then write the rule of the transformation if the general rule g of x equals a times f of 1 over bx minus h close parentheses plus k, given the parameters a equals 1, b equals 1, h equals -4, and k equals 5. And then graph the transform function. And number 4, it says solve by completing the square. Given the equation is x squared minus 4x minus 12 equals y. I'll give you guys some time for that and copy and go, and then I'll go over those with you. Go. See what we got. Sum. Hayden, what'd you get for the sum?
26 plus 2i.
Thank you very much. That's our sum. That is correct. How about the difference, Jaziel?
4 minus 8i.
4 minus 8i. That is correct. That's our difference. How about our product? Alberto. Product. Alberto, you there? Oh, you have, yeah, you haven't done it? Come on now.
I only made the sum of them.
What?
I didn't quite understand the other.
This was the home plate. Product, 15 minus 3i times 11 plus 5i. Okay, Anthony, what'd you get?
That's what it is?
Yeah, product, multiplication.
I got a 165 plus 47i minus 59 squared.
7i. You said 47i?
Yes.
Plus 51i squared. Okay, so up to there so far, yeah, but we forgot to do what at the end? Substitute -1 for I squared. So that means this becomes, let me write it right above, 165 plus 47i, and then minus 51. So what is 165 minus 51? Actually, wait a minute. Yeah, 165 minus 51. That is 104. 114. Is that correct? 114. And then plus 47i. Did we get the computation right? Let's see. 11, 75 minus 33. Isn't it 42?
Yeah.
Yeah, I got 42.
Oh, okay. Yeah, 42i. Yeah, it looked kind of, okay, so 42i. All right. Number 2, solve. Set it equal to 0. We got 2x squared plus 48 equal to 0. I'm going to use square roots. So that means I need to get rid of the 48. So I subtract 48. I end up with 2x squared equals to 48, and it's a negative. From there, we divide by 2. That leaves us with x squared equals negative 24. And last but not least, square root. This cancels this. X equals square root of 24 can be negative 24 can be rewritten as square root of negative 1 times square root of 4 times square root of 6. So what is square root of 4? 2. What is square root of negative 1? I, and bring down the square root of 6. And that's our solution for number 2. Let's go to number 3. For number 3, let me make some room here. They want us to graph the original parent function f of x equals x squared without a table. So let me do that right here. And then by now, this should be automatic. This is x, this is f of x, and our parabola, our parent function should look like this, right there, right there, right there, right there, and right there. Yes? Why, Mr. Q? Well, negative 2 as the domain. What is negative 2 squared? 4. What is negative 1 squared? 1, which is right there. 0, 0, 1, 1, 2, 4. All right. However, they want us to first write our rule given these parameters. So I'm going to substitute for A1, B1, H, negative 4, and K, 5. Now, before I rewrite this, look up to the screen. Look at K. What is K going to do at the end to the entire original function? It's going to move it what? Up 5 steps. Okay, so up. But look at H. What did we substitute now for H? Negative 4. Which direction is that going to leave us to move all the points? To the left, because we're substituting a negative number. That's going to move it to the left. But let's see how it looks now that we substituted it into our function here, our general rule. And by the way, it's a quadratic, so make sure you put a little square right there. Let's rewrite this. G of x equals 1 times f of, parentheses, 1 over 1x. Negative times a negative is a positive 4, close parentheses, squared, plus 5. And now we can write it once more without a function notation here, but we're going to leave it as g of x. G of x equals 1. Do we need to write the coefficient of 1? No. Df, we don't. Parentheses, what is 1 over 1? 1, we don't need to write the 1, so it's x plus 4 squared plus 5. All right, so here we go. We need to move all the points 4 to the left and 5 up. So I'm only going to move the vertex. Look up to the screen. What's the vertex, Mr. Q? Once again, remember when we covered parabolas that the lowest or the highest point was a vertex. So I'm going to move this vertex. That's at 0, 0. I'm going to move it 4 to the left and 5 up. So I'm going to go 1, 2, 3, 4 to the left and 5 up. 1, 2, 3, 4, 5, which is about right there. So my new parabola should be up here somewhere. Same points, but up here. And this is our g of x. But one thing I want to point out, look, it was at 0, 0, the vertex. Now this one is at negative 4 and 5. Now, I want you to look carefully, look up. This vertex was at 0, 0. This one has negative 4, 5. Can your brain tell where we got these two numbers from? Look at the screen. Who sees it? Where did we get those numbers from? Yeah. So where did we get negative 4 from?
H.
And the 5?
K.
That is correct. And I've been doing this very subtly on all these and showing you, and I would say I'm only going to plot this point by itself, and then the rest should follow, because once we get to more transformations, which they're coming, we're going to focus on first plotting just the vertex and then plotting the rest of the points. All right, let's go to number 4. For number 4, they want us to solve using completing the square. So they give us x squared minus 4x minus 12 equals to y. First step, we need to set it equal to 0. X squared minus 4x minus 12 equal to 0. Divide by the leading coefficient, which is 1. And we end up with x squared minus 4x minus 12 equal to 0. From there, we get rid of or eliminate the constant. So that means we add 12, add 12. We got x squared minus 4x equals to 12. To complete the square, we add negative 4 over 2 squared to each side, negative 4 over 2 squared to each side. This is x squared minus 4x plus 4 on the left side equal to 12 plus 4. We can combine 12 plus 4 to give us 16, and the left side stays the same. And then from there, we factor. How do we factor this perfect trinomial on this side? We can use a shortcut, square root of the first, which is x, square root of the last, which is 2, sine of the middle, and square it, and all that equal to 16. And last but not least, we need to take the square root to cancel this squared. Square root, whatever we do to one side, do to the other. X minus 2 equals plus minus 4. Solve for x, so that means we add 2 to each side. X equals 2 plus minus 4. And then we write our two equations. X sub 1 is 2 plus 4, which is 6. And x sub 2 is 2 minus 4, which is negative 2. All right. And let's see who can give me all the 4 names of the, well, I'll give you the first one of what we just found. These are my solutions. What other name do we label it?
X's.
X-intercepts, yes.
Zeros.
Zeros. We're missing one name. Who's got it? Good. They're roots. Yeah. You need to know all those names because we're about to get into the next concept that's coming up pretty soon. And we're going to be needing all those terms as we go about the next section. All right, let's move on. Our agenda for today, we got warm-up number 45 done. We're still working on complex numbers, and home plate for tonight is only pages 135 and 136. Only 135, 136. Your asynchronous code is 7XP5M, 7XP5M. Make sure you're keeping up with your notes and submitting your notes for all this. Your previous home play was pages 133, 134. Make sure you turn that into Canvas. Do that right now if you haven't done so already. I noticed some of you already started doing that since earlier. And once again, your home plate for tonight, pages 135, 136 only. I'll give you 1 minute to do that. Get a Cornell note ready. You do need a Ferrer model. Go. All right. So our objective for today, I can define and compute complex numbers. Once again, in the previous session, we already defined and we already computed by doing addition, subtraction, multiplication, and labeling stuff. But just to make sure we got this on your Ferrer model, write complex numbers, give me a definition, and an example, non-example, and a hashtag. I'll give you some time for that, copy that, and go. 1 minute. So make sure you have your definition, one example, one unexample. By now you should know what they look like, what it says, and so on and so forth. Okay. So just to recap, we started with example 1. I gave you guys a complex number. You needed to label which one was the real, which one was the imaginary. From there, I gave you guys something like this, where it didn't have a real, and we agreed that if it's missing any component, there has to be a 0 there. Okay. From there, I gave you guys, for computation, a practice with 2 binomials first and x. And then from there, we transfer that to just doing variables to make sure that we had our processes down for addition, subtraction, and multiplication. And then I said, well, okay, let's move on to imaginaries or complex numbers now with real and imaginaries. I gave you guys something like this. Is that correct? Yes. And we did plenty of practice. So let's end up with one more. Copy this one, please. Example 3 mega cube. It says, find the sum, difference, and product of, parentheses, 9 plus 17i, close parentheses, and, open parentheses, 12 plus 3i, close parentheses. All right, guys, I'll give you 2 minutes. Copy that and go. See how you do. All right, so let's see what we got for our sum. What'd you get for your sum? Jaziel, thank you.
21 plus 20i.
21 plus 20i. That is correct. Let's go, Jaziel. How about for our difference? What'd you get for your difference? Victor, go.
I got -3
-3
and -14i.
and -14i. Close. Who can see the mistake there?
It should be positive 14.
Positive 14, yes. Thank you. Yeah, because it only distributes to the second term, I mean the second binomial. And remember, this is 17i minus 3i, that's 14. All right, how about our product? Let's see what we get for our product. What you get for your product, Addie?
I'm still working on that one, but I might
Okay.
have,
All right, so then 9 times 12, that's 108. 9 times 3i, that's 27i. Then we distribute the second term, 17i times 12, that's positive 204i. And 17i times 3i, that's positive 51i squared. Can we combine like terms? Yes, right here in the middle. We got 204 plus 27, that's 231i. I'm going to bring down the rest, which is 108. And then we got positive 51i squared. However, are we done, guys? No, Mr. Q. We need to substitute -1. Yes, -1 for the I squared. So I bring everything else down. So I got 108 plus 231i plus 51 times -1. So this is 108 plus 231i and -51. Is that correct? 51 times -1? Yeah. So at this point, let's combine like terms. What is 108 minus 51? That gives me 57. Bring down the 231i and we are done. Hands, have you got that for your product? Yeah, let's go. All right, so hopefully this helped, especially those of you that last night's home play was basically doing this, right? Or the previous night, yeah? All right. So that moves us back to the intro that we did yesterday or the previous time in regards to electric circuits. So here we go. Quick recap. I said electric circuits, the basic one was something like this. And I said, here's a battery, a light bulb, and a switch. And I said a diagram for that, a 2-dimension would look something like this if we would package it to sell it and so on and so forth. Okay. So from there, I said there's more intricate or more complex electric circuits such as this in computers, cell phones, iPads, and every electronic that we use has these kind of electric circuits. And I said, I'm going to introduce you to three components of the electric circuit. And the first one was a resistor. In a resistor, I said, a good way of remembering is that the light bulbs, the old school light bulbs, they have a little wire that breaks after it, you know, so much voltage goes in. And that wire looks like this, like zigzag. And that's the symbol that we use in a diagram for that component, for the resistor. From there, I said an inductor. I said an inductor is basically, if you take, like, for example, a nail, and you get a wire, you wind the wire around the nail. When you wind it, that's why the symbol looks like this, like if you're winding a wire. However, when you wind it and you put power, like a little battery to each of the sides of that wire, it creates a magnet, a magnetic field because of the current that's slowing down, and it's within all that section. And the last one was a capacitor. And a capacitor, once again, I said a capacitor, its function in electronics is to let voltage or current go through, but not allow it to come back the same way it let it flow through. So for example, the capacitor. A capacitor guy, so for example, when you're in, like when I installed alarms in a car, have you guys noticed in your vehicles, most vehicles, when you press the little remote, the lights flash when it arms or when it opens or when it closes the door, it flashes? Okay, so check this out really quick in passing. You're like, oh yeah, so here we go. So a capacitor's job is as follows. So here's, let me draw a nice car right here. Yeah, it's a futuristic car. And here's the headlamp. There it is. Okay. I know, I got skills, right? These are the wheels. Okay. Inside of your cars, there's something that looks like this, a little box. And that box is known as an alarm. And that alarm has a lot of features. So when you press the remote and it does whatever, it comes from there. Well, there's a wire but by the way, it has a bunch of wires. It has a red wire, it has a yellow wire, it has a black wire, it has a blue wire, it has a green wire. But there's this one wire. Most of these alarms have a wire that's white. And that wire has to be connected to the wire of the headlamp in your car. Headlamps usually have two wires, one positive and one negative. So when we plug this in, connected to that positive, whenever you press the remote, here's the remote, on, off. When you press this button, it sends the signal, and that's why your lights flash when you press the remote. However, check this out. In order for us, the people that install these, professionals, for this little brain not to burn, we put a little capacitor right here. We installed one because it's going to allow current to go in that direction. But whenever you turn on the headlamps at night on your car, it doesn't allow that current to go back and burn your brain down over here. Does that make sense? It only allows the signal to go out, but doesn't allow it to come back. That's why that symbol right there, it's like a little stop sign, like bam. All right, enough of that. All right, so then yesterday we got to this point where I had you guys copy the diagram for a circuit, and then we labeled it. Is that correct? Okay. And we said that this was the what? The resistor, this is the inductor, and this is the capacitor. And then for home play on your asynchronous, you needed to do one of these. Is that correct? Copy this one. We're going to do this one together. Copy that. 20 seconds. All right, let's see where we're at. Example 4Q, it says label the electric circuit. You should have sketched this diagram, and basically it's a big rectangle. And there's here, this part is voltage. Okay. Now, so that you can put it in your brain and understand what we're looking at, this could be, look up, this could be your room. This could be the living room, and this could be the hallway. And within those three, that becomes a circuit at your home. And it has certain components like these that we should know by now. So check this out. I'm going to start with this one. What is that? Jesus, what do we call this one?
It's called the inductor.
Inductor, that is correct. All right. How about these, Danny?
Resistor.
Resistor. All right. And last but not least, guys, these are called capacitors. And in short, whenever we're working out in the field or doing installations, whatever the case, just to make it a little bit faster in our communication, I'll be under the car, like installing the alarm, and I'll be like, hey, can you get me a cap, please? So instead of saying capacitor, we just call them caps, and so on and so forth. So it's part of the lingo. All right. So now that we know what we're looking at, look at this one. By the way, you did these for a home play, is that correct? Yes, Mr. Q. All right, don't copy this one, but let's see. Let's see if we see, if we understand what we're looking at. So once again, wherever you see an opening here and it has an arrow or something that is a circle with a little symbol, that means voltage is going and it's starting voltage through there. Okay, so what do we have here? This is a capacitor. What do we have here, here, and here? These are resistors. And what do we have over here? This is an inductor. Okay, so far so good, yeah? Show me your fingers, how come you are with these so far, labeling and understanding what we're looking at? Yeah, 5s. Yeah, okay. Look at this one. Do we know what we're looking at now? Yes? Okay, so what is this one and this one? This one and this one, Dominique. This one and this one. What are these called?
I'm not sure. The resistor.
The resistors over here, the zigzag. These two right here.
I'm not sure.
Okay, Gemily, what are these called? Victor, help her out.
Inductor.
Inductor, resistor, inductor, capacitor. Okay. Now, once again, guys, I gave you guys plenty of practice last night with these in your synchronous. If you didn't do it, you're probably going to be like overwhelmed with what's coming right now. It's going to get really interesting really fast. Okay. So here we go. Here goes a quick intro to electric circuits. Ready? Let's talk about electrical current. Ready? So all of you know that in this world, there's a lot of power. Yes? Now, there's two types of power that I'm going to talk about today. Electricity. There's the one in our home, and there's the one that we use in our cars or in our cell phones inside that have just a small battery. There's two different things. The one in our home comes from the big old cables that are run through each city, throughout the state, and throughout the nation. All right, that kind of energy, guys, that is inside of our home is known as alternating current. Write that down. AC, or alternating current. Now, in a simple way of explaining this is as follows. Alternating current, let's say on your wall, you have an outlet that looks like this. Is that correct? Yeah. And you start freaking out when your cell phone, it starts running out of juice. So here's your charger for your cell phone. Has a little wire. Here's your cell phone. Well, let me make it bigger than the outlet because now the phones are like almost the size of our hand or bigger. There it is. Here's our phone. There it is. Okay. So you plug in your charger to your phone and then you plug it into the wall. Is that correct? All right. So check this out. Do you guys ever notice that most of the times you don't really care which direction you plug it into the wall? Did you guys ever think about that? Let me tell you why. Because these two, when they plug in here, one of them is positive, the other one is negative. However, since you switch them, like you don't care about the direction, sometimes then you can switch this one to be negative and this one positive. So what do you guys notice? That either one could be positive and negative. That's why it's called what? Alternating. You can alternate which one is which. And the voltage coming in through there is 120 volts or 220 volts or 240 volts. It's a lot of voltage. That's why you learn since you're early as a kid, they tell you not to put anything in the outlets because you can get electrocuted. That's a lot of power. A lot of power. A lot of power. Please do not play with any electricity if you don't know what you're doing because it can kill you guys. Just letting you know. Okay. The second current or electrical current is known as direct current. Direct current is when it involves pretty much batteries. Batteries. Okay, what does that mean, Mr. Q? Well, in a car has a battery that looks like this, and it has a positive and a negative. In your cell phones, the cell phones have a very thin battery that's rectangular like this, and it still has a positive and a negative. So thin we don't even see it. It's inside in our cell phones, the iPads. However, there's some of you still have maybe karaoke machines or radios, and they take like C batteries. Here's this is a C battery. It takes a lot of them. You put them you stack them like that. Another C battery. Anyways, all these batteries have a positive and a negative. All these are direct current. What does that mean, direct current? That we cannot switch these and say, oh, I don't want this to be positive anymore. I want it to be negative. No, because if you do that, you'll burn out whatever it is you're connecting. If you switch them the other way around, it's going to burn whatever you're connecting to it. Now, most of the mistakes that people make when they install car stereos and alarms, and when they go to install the two wires finally at the end to make the system work, when they switch these around, sometimes they burn out a fuse or they burn out the whatever they're installing. So that's why these cannot be alternating. This one can, so it doesn't matter how you connect your charger on the wall. This one does need to stay this one positive and that one's negative. That's why it's known as direct current. All right. Now, there's a way of measuring a certain current going through a circuit. When we measure that, it's known as an impedance. Write this down. Impedance is the amount of current that can be and flow through an electrical circuit. So pretty much it's like this. Whenever, to put it in more of your perspective, imagine you go into the grocery store. You know how sometimes grocery stores have very flimsy plastic bags, but they also have stronger plastic bags. Is that correct? So if I asked you to put 5 pounds of oranges in the flimsy bag and it rips, You put the same amount in the stronger plastic bag, and that one doesn't rip. It stretches, but it doesn't rip. That's what we call impedance. I guess the resistance of how much it can go into the bag without breaking it, okay? Now that impedance, here it goes again, the impedance of that current going through is known as ohm. We use the unit of measure of ohm, and here's a symbol that we're gonna use. It's a Greek letter. So for right now, we're just, think about it, that we're gonna, instead of saying impedance, we're gonna say ohms. So let's say something has 5 of impedance, then we're gonna say 5 ohm. If I say that one only has 1 of impedance, so then it's 1 ohm. And here's a symbol. All right? All right, let's see what we're talking about. So, according to what we wrote in our table, we have a resistor, inductor, and capacitor. Yes? Yes, Mr. Q? All right, now check this out. Now we're gonna start putting numbers and values to each of these because there's a purpose that I'm giving you this introduction, because now we're gonna start using complex numbers. You're like, what? That's used in electronics? Of course. So a resistor, inductor, and capacitor, we're going to represent those with the following. A resistor is represented with a real number. An inductor is represented with an imaginary number that's positive, and a capacitor is an imaginary number that's a negative. Okay? Write that down, please. All right, I'm gonna place this diagram on the top left. You already have the first 2 columns from your notes. You're just adding the last description, right? And I want you to copy this next circuit and this next table. So the circuit's over here to the right. Copy that and copy this table. The table is a 2-column table, and it's the left side is circuit components titled, and then we have resistor, inductor, capacitor. And on the right side, it says impedance. Copy that, I'll give you 1 minute. Go. All right, here we go. So for those of you that didn't do the practice on your own, like I asked you to on your asynchronous assignment, let me label this one more time to make sure that we understand what we're looking at. It says here the resistor, this is a symbol. So if I look at my diagram here that they gave me, that means this is a resistor. Okay. From there, I look at the other part, the other component, this one, this says this is the inductor. And the last one, which is this one, this is my capacitor. Okay. And now notice, now they give us impedance. The impedance for the resistor is 4 ohms. The impedance for the inductor is 3 ohms. And the impedance for the capacitor is 5 ohms. So we're going to write that with complex numbers here in our table here. Here we go. Let's start with the resistor. The resistor, they give me 4 ohms, but it says here in our table that it's represented only with a real number. So what is the real number that I can write that with? 4. All right, next I'm going to go with the inductor. Inductor is 3 ohms, and it says it's represented with imaginary number, and B has to be greater than 0, which is positive. So if it's 3 ohms, then I write 3I. Capacitor. The capacitor, its impedance is 5 ohms, but it says here that to translate it, it becomes an imaginary number, B less than 0, which means it's a negative. So if it's 5 ohms, I would write what? 5I, and it's a negative. Are we there so far? Yes? All right, show me your fingers. How come you are up to right there? Yeah, so we know how to label the diagram. We know how to write our impedance. I'm going to give you one for you to do by yourself, okay? Here it goes. And on this next one, if you don't want to redo the table, just add a column right here for this next one that you're going to do. And just write impedance again for this new diagram. Here it goes. So this new diagram, it's on your screen, example 5. Here it is. And if you notice, it has 120 volts. That this could be a diagram of a home, and this is a circuit of a home. So label it, and then from there, write me the impedance. Copy and go. All right. So let's see, I'm gonna label my impedance. Now I'm gonna use just black, because by now I should be able to know what I'm looking at. So for my capacitor, what am I gonna write right here for the capacitor? I see the capacitor is 10 ohms. So that means this is negative 10I. Hands if you got that. Good, okay. My inductor is 7 ohms. So that means the inductor is translated into imaginary, so this is 7I. And lastly, my resistor is 9 ohms, and it's a real number, so I just write 9, it's a constant. Hands if you got that. Okay. All right, so check this out. Next, don't copy this, but once again, the resistor, what would I write here? Let's look at the resistors right here, 5 ohms, so I just write 5. Inductor, 8 ohms, 8I. Capacitor, 7 ohms, negative 7I. Okay? Look at this one. Look up. You're like, oh man, Mr. Q, yeah, this is example 5 mega Q. This is more intricate. Here we go. Look what I'm gonna do. Look up. I'm gonna start with my resistor. Can you picture the resistors on the diagram? Look at them. Look what I'm gonna write for my impedance. Does everybody see what I did? Yes? So what would I write for my capacitor? Capacitor. What do you think, Esmeralda? Negative 5I, that is correct. 2 plus 3 ohms, that's 5 ohms, and it's a negative 5I. That means that for my inductor, we only have one there, that's 7I. Okay, all right. So I'm gonna have you go, you can do this one on your own once again from the session for your synchronous. Fill that in on your own, but I want us to get to this next section, the final section that you're gonna need for your home play for tonight. Ready? Copy this down. Here's a formula to compute the voltage of any circuit. Here it goes. To compute the voltage, they give us the formula V equals I times Z. Here it goes again. To compute the voltage is I times Z. So V for voltage, I is the current in amps, and Z is our impedance, which is the one that we just did right now, the labels that we did, okay? I is current in amps, and Z is the impedance, which is what we just wrote for each of the components, okay? So what we're gonna do, I'm gonna give you a diagram, and we're gonna figure out how much voltage is going through each of the components, and they are going to give us how much current is going in, okay? So here we go. Copy this. Example 6, you have the formula, copy this component, this circuit, and then we have in red 24 plus 12I, which is our current that they give us. This is given, and in the home play they're gonna give us the current, and then we're gonna make a little table like so. First column, it says circuit component, resistor, inductor, capacitor. To the right we have a column that reads impedance, and then to the right of that, the voltage. All right, so once again, this in red is the letter I, which is the current. That's given to us that we're going to substitute into the formula. The letter Z, if you notice it's in green, that one is our impedance. And we know how to label that from the diagram. Is that correct? Yes. So basically, we're going to take this formula, check this out, I'm going to write it here, V equals I times Z, which is our impedance for each of the components to find out how much voltage is going through them. But before I do, I want to know all my impedance given this diagram. So by looking at it, let's look at the resistor. It says 4 ohms. So what would I write here? It's a real number, so I just write the number 4. Inductor, where's the inductor? It's over here. It says 3 ohms. So how would I write that? 3I. And lastly, the capacitor. The capacitor is down here is 5 ohms. And how would I write that? -5I. All right, now that we have that, now we get to work. Ready? Here we go. Let's get our, let's find out how much voltage is going through the resistor. So let's use this formula. So I write V, oh, sorry, change that. I'm gonna write V equals, what is I? Oh, I is the current, which is 24 plus 12I times the impedance. What is the impedance? 4. Okay, once I have that, now I just need to do distribution. 4 times 24, that's 96. And 4 times 12I, that's positive 48I. And that's the voltage going through the resistor. You're like, oh, this is easy. Yeah, all we have to do is know what we're looking at in the impedance. Let's do the next one. Voltage equals, what is the current? The current is 24 plus 12I, which is the same current. We're going to multiply that times, what is the impedance for the inductor? 3I. All right, let's distribute that. Distribute, distribute. Let's see. 3I times 24, that's 72I. Oh, forgot to write voltage, sorry. V equals 72I. And then 3 times 12I, 3I times 12I, that's positive 36I squared. However, what do we know whenever we see an I squared, guys?
-1.
Yeah, we substitute -1 in here. Okay, so let's start with that. And that leaves us with, let's see, our voltage. What is 36 times -1? That's -36. And we're left with the other one, which is positive 72I. That's the voltage going through the inductor. Let's see, find me the voltage going through the capacitor yourself. All right, let's see what we got. The impedance is 5I. So if we distribute that, distribute, get -5I times 24, that's -120I. And -5I times 12I, that's -60I squared. But what do we know? We need to substitute what? -1 in here. Therefore, my voltage going through the capacitor is -60 times -1, that's 60, and then -120I. And that's how you compute the voltage for each component. Now, in the home plate for tonight, guys, they're going to give you a diagram like that, and they might ask you just to find one or two different components. Here I gave you all three of them, and I showed you how to do the work. So with that said, how comfortable do you feel with this so far? See if I'm 5 4s, 5 4s. Yeah, we got this. Yeah. So for tonight, pages 135, 136, make sure you do the practice. Tutoring after lunch, be there or be elsewhere. Peace. Have a good one, guys.
Bye, Mr. Keo.
Bye. Have a good one.